So, welcome students to this edition of our recorded class. In this class, today we will talk about the new chapter of our study of dynamics of rigid bodies, and that is going to be our work energy equation. So, we have already studied the basic principle of work energy equation in connection with the particles, and then we extended that concept from for a single particle to a system of particles also. And now today we will be extending our concept of the principle of work and energy to a rigid body and a system of rigid bodies as well. So basically, you know that when we will be going to write the work energy equation in connection with a single rigid body, we have to remember the associated kinematics of that single rigid body. As we know that the kinematics for a single rigid body can be a pure translational motion, it can be a pure rotational motion, or it can be a general plane motion or GPM, which is nothing but a combination of the translational motion and the rotational motion. We can consider that the rotation can be considered as with respect to the center of mass, though this GPM can be considered the rotation with respect to any fixed point, any point on the body, but in this case we will consider it to be the rotation about the center of mass of the body. So if we recall our basic the integrated work energy equation which we had derived in connection with a system of mass particles, but we are going to write that same equation in connection with a single rigid body, and this time we have to remember that a rigid body can be subjected to not only the external forces, it can be subjected to the external moments as well. So keeping this in mind, we see that our basic integrated work energy equation can be expressed in this form. It is delta T, which is the change in kinetic energy, plus delta Vg, which is the change in gravitational potential energy, plus delta Ve, which is the change in elastic potential energy, should be equal to 1 U2, which represents the work function by the external forces, and in this case it needs to be revised that it is also subjected to external moments, so therefore it will be the work done by external moments also. That means this 1 U2, which is called the work function, that includes the work done by the external force F bar dot bs bar, the integration from S1 to S2. This is the work done by the external force F bar, and plus to it we need to add the angle theta 1 to theta 2, this integration m bar dot d theta bar. Now in this equation we have to remember that theta is the rotation, angular rotation. In this case we can consider it to represent the angular displacement, but since theta being a finite angle, it cannot be treated as a vector quantity, but the differentially small angle is a vector. So therefore, unlike the case that the displacement is a vector quantity as well as its differential form, in this case we see that the entire the differential of the infinitesimal small angle is therefore a vector quantity. So this is how we can write our work energy equation, and the work function can be extended from the concept of the work done by the force to the concept of the work done by the moment. So it is the dot product of these two. So in the above equation we need to remember that the subscript 1, it indicates the initial configuration of the rigid body, and subscript 2 refers to the final configuration of the rigid body within the window of which I am going to basically write or apply the work energy equation. We have to remember that the situation when when it is conducive for us to apply the principle of work and energy that we have already discussed in connection with a particle and a system of mass particles, we reiterate that the principle of work and energy is basically a bypass of our classical Newton's method. Particularly, this situation is very much effective when our forces and moments are known to be functions of position and displacement and everything, and when our basic intention is to find out the velocity of our system. So therefore, in those types of problems, basically, the work and energy principle can be profitably used to as an alternative to the more elaborative method of classical method of Newton's force analysis and moment analysis as well. And this is the first thing, that therefore you see the situation system, the subscript indicates, the one subscript indicates the initial configuration and the two subscript indicates the final configuration of our rigid body. F bar here is the external force acting on rigid body as shown in the active force diagram. So this is again a very advantageous situation of this method, that we do not have to basically deal with the free body diagram. Remember that a free body diagram encompasses all possible external forces and reaction forces, moments, etc., which may be acting on a body when I isolate the body in question from its surroundings. However, a large number of forces as exposed in the free body diagram are actually called the reactive forces or reactive moments, in the sense that they do not contribute into the work function. That means when these forces are or the moments are actually that they are perpendicular to the corresponding displacement vectors, or if they are associated with the immovable support points, support reactions, in those cases you see that because of this peculiar dot product of these two vector quantities, we find that those forces are incapable of contributing something meaningful to the work function. As a result, such types of groups of forces or moments, as the case may be, will be treated as the reactive force or reactive moment, and in that case they will not basically contribute into the work function, and we can actually do away with those groups of forces or moments from our free body diagram. So the number of forces and moments that we need to consider for calculating this work function will be limited, and therefore we have a subset of the free body diagram, which is the active force diagram. So we need to only focus on the active forces as shown in the active force diagram, which contribute to the non-zero work function in work potential into the work function. So we see that similarly a bar that represents the external force, m bar represents the external moment, and ds bar and d theta bar are respectively the displacement and linear displacement and the angular displacement in connection with those line of action or in connection with the point of applications of those forces and moments. Now delta Vg, as we know that it represents the gravitational potential energy, and delta V represents the gravitational elastic kinetic potential energy. So this about them we will discuss little later. Another thing that is to be highlighted here is the fact that this one U2, which represents our total work function, must include the forces other than force due to gravity and forces due to the springs. Why it is so? Because the work done by the force due to gravity and force due to spring, we know that these forces, I mean to say the gravity force and the spring forces, linear spring of course, they are basically conservative in nature, and thus they have some potential function associated with them. And we can take care of the work done by such conservative forces in the form of their potential change in their potential functions, and therefore their work done has already been taken care of in the left hand side of this equation. So in the right hand side, when we are going to write this work function, we must exclude that from that active force diagram. We must exclude the forces due to gravity and the forces due to the springs, elastic linear springs, which will be generating over there. Now, regarding the most important thing about this is that in this equation is about the kinetic energy expression for a rigid body. So if you recall, actually the kinetic energy of a rigid body which is undergoing, let us consider that it is undergoing a general plane motion. Okay. So in that case, that means it is a general force equation, general kinematics of the rigid body. So as we know from our discussion from the group of mass particles, as we have already been reiterating onto this fact that the dynamics of system of mass particles is basically the the introduction or the foundation to study the dynamics of rigid bodies. So there, if you recall that when we studied a group of mass particles and moving with arbitrary velocities associated with the different mass particles, we noted that the total kinetic energy of that system is given by half mv bar square, which represents the translational kinetic energy corresponding to the system center of mass of the system, and this m represents the total system's mass. To it we need to add the individual relative velocity that is associated with individual mass particles, and we said that it is mi v relative I square. And in case of system of mass particles, this mi or the the discrete mass particles are discrete in the sense that it will be say running from 1 to n, where n being any number. But in case of a rigid body, these mass particles are what is called, they are continuously distributed and the sum is infinite. So this sum basically converges to an integration. So for a rigid body, I can write that the kinetic energy is being given by half mv bar square, where m represents the mass of the rigid body, v bar represents its velocity of its center of mass, and this represents the relative kinetic energy, and we can say this is half integration m v relative square dm. So let us consider that this is the rigid body whose center of mass is somewhere here. This is the center of mass, it's called C. Let us identify a differential mass dm arbitrary at a distance of rho from the center of mass. Let us assume that the center of mass's velocity is v bar. Then we know that with respect to a translating reference frame which is associated with or attached with the center of mass, the relative velocity of this differential mass particle will be given by omega bar cross rho bar, where omega is called as the angular velocity of the rigid body. And we have to remember that we are basically dealing with the plane motion of the rigid body, in the sense that the angular velocity vector is going to be perpendicular to the plane of motion of the rigid body. So omega bar will be going to be perpendicular to this position vector rho bar that is there. So I therefore say that the relative velocity for this mass particle with respect to the center of mass of the body is being given by omega bar cross rho bar. And when we are trying to calculate the square of the relative velocity, basically we are going to take the magnitude of this vector square. So we can write it like this. And particularly remembering the fact that our omega bar and rho bar are orthogonal vectors for plane motion, I can see therefore that the magnitude ultimately boils down to a very simple thing, that it can be written as omega square rho square. So if we see, this is the relative velocity square, and if I insert it into this integration, then we note that the relative kinetic energy with respect to the center of mass is being given by half integration over the entire domain of the mass m, v relative square dm, and in place of v relative we put this, and you see that this omega being constant with respect to the, because it is constant for entire body, so I can take this omega square outside of the integration and can write this integration as half omega square, the integration over the entire mass rho square dm. And already we know that this integration for a slab-like body, if we consider this rigid body to be a slab-like one, that means the body which is having a very small thickness in its perpendicular direction, we can say that this integral represents the mass moment of inertia about an axis which is perpendicular to the plane of the rigid body. That means perpendicular to the plane of the plane of motion and going through the center of mass. So we can call it as centroidal mass moment of inertia, define it by I bar, and thus we can see that our total kinetic energy of a rigid body can be, for a general type of motion, can be expressed into this format, that T equals, that is the total kinetic energy of the rigid body at a particular instant when its center of mass's velocity is known to be equal to v bar, and when the instantaneous angular velocity of the body is known to be equal to omega. At that particular instant, the total kinetic energy of the rigid body will be given by the equation T equals half mv bar square plus half I bar omega square. So this component, this first part will represents the translational kinetic energy associated with the total mass being concentrated at the center of mass location of the body, and thus the mass will be moving with the center of mass's velocity. So this is what is termed as the translational kinetic energy, and the relative kinetic energy of the individual mass particles with respect to the center of mass ultimately boils down to the equation that it becomes half I bar omega square. So this together, added together, will give me the total kinetic energy, and it can be viewed as to be the sum of the kinetic energy due to translational motion and the kinetic energy due to the rotational motion. So with this background in mind, let us now further consider that for a single rigid body subjected to multiple active forces, which are of course other than the spring forces and force due to gravity, the full work energy equation that we have already seen in the form delta T plus delta Vg plus delta V equal to 1 U2 will take this equation, the kinetic energy delta T will be half mv bar 2 square plus half I bar omega 2 square, which represents the final total kinetic energy of the rigid body, minus this is the final total kinetic energy of it represents the initial total kinetic energy of the rigid body. So this will be the difference. So this equation represents basically, this two term represents basically delta T. And now if we consider the center of masses location of the rigid body at the two different situations, I mean to say the initial configuration, if we can isolate the center of mass and its location with respect to certain pre-selected reference frame, if we call that height of the center of mass as h1 bar and the final height as of the center of mass as h bar 2, then this represents basically delta Vg. This is mg h bar 2 minus mg h bar 1. So it basically represents Vg at situation 2 and this represents Vg at situation 1. Now assuming that I have altogether, that there are, suppose in this single rigid body, let us suppose that there are say m number of linearly elastic springs that are associated. That means in this case, whatever springs that we will be talking about, unless mentioned otherwise, will be treated as to be the linear spring. So there is no question of nonlinear spring over here. So in this case, we see that it represents summation j from 1 to m. Suppose there are m number of springs are there. So therefore, delta VE will take care of this format, that it will be half kj xj square for situation 2 minus half kj xj square for situation 1, and this difference needs to be summed for each and every spring which are associated with that single rigid body. Therefore, this term, I reiterate, it represents delta T. This term, I say that it represents delta Vg, and this term, it represents delta V of the single rigid body, and that should be equal to summation I from 1 to n integration f bar I dot ds bar I plus summation j from 1 to p m bar p dot d theta bar p. It is because that single rigid body may be subjected to many active forces, may be subjected to many active moments, which meaningfully contribute. They can meaningfully contribute into the work equation. So therefore, this total represents the total work done by the active forces acting on a single rigid body as disclosed in the active force diagram, and this represents the total work done by the active external moments which act on the body, that to contribute in, and they have a meaningful contribution into the work energy equation. So this is we see that this is applicable for a single rigid body. We see, however, we see that if there are a group of interconnected rigid bodies, so thus far whatever we are discussing, we see that we have been, thus far we have been discussing about what is termed as a single rigid body. And now if we have a group of interconnected rigid bodies, say for example here there are a group of interconnected rigid bodies are there. So these are, this is the hinge point with which this rigid body 1 is interconnected with another body 2, and then it continues, and suppose there are n number of such bodies which are there, and each body is subjected to a group of external forces and moments may be acting in the system. And let us assume in this case that the joint forces, that means if we single out a particular body, say suppose if we single out body 1 from the entire group, then there will be the joint reaction forces which were thus far are internal in nature will be now exposed. So you will be getting the joint reaction forces. In a similar way for body 2 also, if we draw the active force diagram, then again that joint internal force will come, which will be for body 1 and body 2, which will be action reaction pair, and for other bodies also it will be like that. And since all these say for example, if we take the case of body 1 and body 2, let's suppose that we have only two bodies, interconnected bodies. So in that case, the common point at which the two bodies are being connected with each other, they suffer the same displacement during the change of the configuration of the system. And since they suffer the same displacement, that means the displacement on body 1 and displacement on body 2 is basically same. That means there is no change in relative, that means their relative displacement is 0. That means as long as there is no relative displacement between the two, we see that the total work done by the internal forces will be equal to 0. We have elaborated this particular thing when we discussed, if you recall, our system of mass particles class. There we had discussed it in detail and shown you how we can have the total work done by the internal forces, and this under this condition, when the displacement, there is no relative displacement between the two bodies, we see that the internal force work done is totally equal to 0. However, we made a very careful observation that it may not be true always. So we see that in this case, in our present case, since the displacements are identical, so we see that there is no work done by the internal forces. So we see therefore that if we write our equation, assuming that there are n number of bodies here, so the above equation that we had written for a single rigid body, we see that this is the equation for a single rigid body. Now we have to write the same equation for all the rigid bodies which are the part of my system, interconnected rigid body system, and therefore this will be preceded by a grand sum, and the sum needs to be taken for the entire rigid bodies which are part of our system. So this is our basically the work energy equation. Now before we proceed further, let us now make certain observations which are will be helpful for us when we will be dealing with the problems. And these are the cases that how the kinetic energy, what will be the form of the kinetic energy under the different kinematic situations of a rigid body or a group of rigid bodies. So in case that, let us consider we discuss it for a single rigid body, and then it can be very easily extrapolated for a system of rigid bodies. So if we let us for the time being consider a single rigid body, and if it is supposed that that particular rigid body is undergoing a pure translational motion, in that case the kinetic energy of the body will be simply given by this equation, because for pure translational motion obviously there is no angular velocity associated with it. Now let us consider the situation when our rigid body is undergoing a pure rotation. And if you recall that the pure rotation can be of two types, that the pure rotation about a fixed axis, it can be of two types. In the first case, the fixed axis which is called as our axis of rotation passes through the center of mass of the body, or in other words, we say in that case that the body is executing a centroidal pure rotation, fixed axis rotation. So in that case, we see there will be no velocity, linear velocity of the center of mass, because the center of mass is belonging to the axis of rotation. And in that case, the entire kinetic energy will be written as the pure, which is called the pure rotational kinetic energy. In fact, the above kinetic energy, we call it to be the pure translational kinetic energy, and in this case it will be pure rotational kinetic energy, and we have to use this I bar, that means the mass moment of inertia of the slab-like body, which is about an axis which is passing through the center of mass and perpendicular to the body, plane of the body. Now we can have another situation where you see that the same rigid body can undergo non-centroidal rotation. That means in this case we have, other than the center of mass, we have some other point as the center of rotation. So let us consider, for example, this is in the picture. Let us consider this is an arbitrary slab-like rigid body which is rotating, undergoing rotation about the fixed point O, which is not the center of mass of this body. And let us suppose this is where the center of mass is, and the distance or the position vector of the center of mass from this is basically r bar. So in this case, you know that the center of mass will be definitely having a velocity, because if this is the sense of the instantaneous angular velocity of the body, then we can definitely say that our center of mass's velocity at that instant will be obviously given by this vector, which is going to be perpendicular to this r bar, and this is omega bar cross r bar. Or for the general plane motion, we see that its magnitude will be basically, if we consider its magnitude, the magnitude will be equal to omega into r bar. So that is our going to be the velocity of the magnitude of the velocity of the center of mass. So if we take v bar is square that represents the the square of the magnitude of the velocity. That means you can say it is the speed of the center of mass. So we see that it will be half m omega square r bar square plus half I bar omega square. From here I can take half I bar square half omega bar square common, and this expression can be written as I bar plus m r bar square into omega square. And from the parallel axis theorem, we can say that this I bar plus m r bar square basically can be written as IO. That means the mass moment of inertia of this same rigid body about an axis which is perpendicular to the plane of this slab-like body, and it passes through the point O, and it is not the centroidal axis of inertia. So it is called the non-centroidal axis of inertia. In this case, the moment of inertia needs to be calculated with respect to the center of rotation about which the rigid body is undergoing pure rotation. So you see that in this case we can write the kinetic energy. This could be an alternative form, that T equals this could be the alternative form, or the other form which will be more convenient for us to apply is simply take the angular velocity, because in this case we need to take into account both the center of mass's linear velocity as well as the angular velocity of the body. In this case, we do not have to bother about the mass center's velocity, and we can simply write the total kinetic energy is purely due to rotation, and that can be written as half IO omega square. So this 2 and 3 together, they define the case when the rigid body is undergoing pure rotation, either with respect to the centroid or with respect to any non-centroidal point. Now let us come to the last situation where we have to deal with the GPM, general plane motion. Now in this case, if we are able to locate, suppose when a rigid body is undergoing a general plane motion, that means when we have the body center of mass is having some velocity as well as the body is having the angular velocity, just like this one, this can be also considered as a special case of GPM, correct? Because it comes under the definition of GPM. So in this case, if we can find out the instantaneous center of rotation, in this case you see this is actually the permanent center of rotation. Okay, but in case of GPM, this point O will not be fixed one. So in that case, we see we will be having instantaneous center of rotation of this body if we can locate it conveniently, and if it is convenient for us to geometrically locate the instantaneous center of rotation about which the rigid body can be assumed to be rotating with respect to that point instantaneously. For that particular instant, I can calculate the kinetic energy assuming that it is undergoing pure rotation about it, the instantaneous center, and as a result the kinetic energy can be written as half I. Now this time it should be taken about an axis passing through the instantaneous center, so I write it half IC omega square. If it is not possible or if it is inconvenient to locate the instantaneous center, because it may not be possible all the time, or even if it is possible, the associated geometry may not be very conducive for us, in that case, of course, we can apply the general equation of the kinetic energy, which is is being given by this particular thing, which is going to be true under all circumstances, and therefore we can treat this equation as the most general representative equation for the kinetic energy of a rigid body. So with this background, theoretical backgrounds in mind, let us now embark and show some examples which actually try to elaborate the application of the theory so far we have studied. So let us begin with our first example. This problem is taken from the book of Merriam, and the problem is the problem number is 6/114. Let us go through this problem first. In this problem, what is shown is that a log, this is the log, it may be a wooden log, is suspended by two parallel 5-meter cables. So these are the cables which are 5-meter long, and the identical cables, and is used as a battering ram. So it will come and try to hit someone. So it is called a battering ram. So at what angle theta should the log be released from the condition of rest in order to strike the object to be smashed? So this is the object to be smashed, because we are using it to be a battering ram whose objective or whose duty is to smash certain objects. So this is that object to be smashed, and this ram is going to come and hit that object for smashing. So we need to find out the angle which will ensure that this battering ram is going to strike the object to be smashed with a desired velocity of 4 meters per second. So we need to find out this angle theta from where this log needs to be released so that it comes and hits it with this velocity. So we see from the kinematics that this is actually is a single rigid body. This log is a single rigid body. Number two, these are the observations that we need to do regarding the problem. And number two, the associated kinematics is curvilinear translation. So there is no change in orientation of the ram. So you can see this initial configuration and the final configuration of these two, they are parallel to each other, which means that there is no change in orientation. So it means that there is no angular velocity associated with the motion. So we can understand that this is going to be a translational motion. In this case, it is going to be a curvilinear translational motion. So if I call this initial configuration from where the battering ram was released with no velocity, if I call this configuration as 1, and this is going to be my final configuration, that means the position which is shown as dotted line, the final position of the ram has been shown with this dotted line. We take this position as our position number 2, which is going to be our final position, and for purpose of calculating the gravitational potential energy, we know from our knowledge of the work energy equation that we have used in connection with a single particle or a group of particles, we know that this particular calculation of the gravitational potential energy requires the specification of the datum level. That means where we consider that the gravitational potential energy is 0, and this is completely arbitrary assignment, and anything above is to be taken as plus, anything below is taken as to be minus. So the assumption of the datum line is going to be completely arbitrary. Anyone can take any suitable, the configuration of the system as to be its datum in order to calculate the change in gravitational potential energy of the system. Secondly, we need to note that apart from the self weight of this RAM in this system, we do have the tensions that are associated with the strings. However, if we do not cut the strings and remain as it is, keep them as it is like that, they remain internal. And even if we expose them, we see that the displacement of their point of applications, displacement vectors, they are going to be perpendicular to these tension forces. Because if we release, suppose if we consider it like that, this is the point of fixation and this is the string, and when we are releasing it, that this displacement will be, this is going to be perpendicular to the tension, right? Tension is radial and displacement is tangential. So the angle between them is going to be 90 degrees. So as a result, we see that the tensions associated with the strings are actually reactive forces and not contributing anything into our work equation, and therefore they are not the part of our AFD. Having recognized this, we also note that apart from the gravitational force, there are in fact no external forces associated with our system. Number two, that we note that there are no springs, so there is no question of considering the elastic potential energy to our one. So now peacefully we can apply our work energy equation between these two configurations 1 and 2. Therefore, we see that since we do not have any other force other than force due to gravity here, so 1 U2 will be basically 0. So as a result, we see delta T plus delta Vg is going to be 0, which means that sum total of kinetic energy and the potential energy, gravitational potential energy, they are going to be constant, or the energy is going to be conserved. So I can write this equation as T2 plus Vg2 is equal to T1 plus Vg1. And if we put all these values, we can see that V2 square becomes equal to 2gh, where h is, of course, we can write it h bar. We should write it h bar. H bar represents the height of the center of mass. In this case, the height of the center of mass of the battering ram, in this case, which refers to this center line. So from the pure geometry, we can find out from here that our h bar, that means this h bar, we can see it here, it will be equal to, we can write it from the associated geometry that this h bar is going to be equal to 0.5 minus 0.5 cos theta. So we can say that it is going to be equal to 0.5 whole into 1 minus cos theta. So this is going to be our h bar. So we see therefore that V2 square is equal to 2h bar, and on substituting this value of h bar, we find that cos theta turns out to be 0.834. That means theta is becoming equal to 33.19 degree. So it means that the system needs to be released initially such that the strings must make an angle of 33.19 degree with respect to the vertical, so as to, when it comes, the strings becomes perfectly vertical, the ram would acquire the desired velocity of 4 meters per second with a view to smash the particular object which it is supposed to smash. So, dear students, I think that this simple problem will exemplify you and we will clarify you how we are going to apply our work energy equation in connection with a pure translational motion. Now let us move on to our next problem, where you see that this problem comes to under the category 6 by 120. Let's see what is the problem. So this is the problem figure that has been shown here. What is the statement of the problem? It's going the 1.2 kg uniform slender bar. So this is 1.2 kg uniform slender bar. So this is going to be my rigid body. So again we have a single rigid body, okay, and it rotates freely about a horizontal axis through O. So you see that this is the case. It is in vertical plane because the axis of rotation is horizontal. So surely it shows that it is in vertical plane. So acceleration due to gravity is acting in the downward direction. And also we see that it is a case of fixed axis non-centroidal rotation. The system is released from the condition of rest when the rod is in horizontal position with theta equal to 0. So you see this is the angle which represents theta. So when theta is equal to 0, that means when the rod is in the horizontal position, at that situation the spring was unstretched, where the spring is unstretched. So at the situation when the rod was horizontal, the spring was totally unstretched. If the bar is observed to momentarily stop when released after releasing from this horizontal configuration with 0 velocity, if the bar is observed to momentarily stop in the position theta equal to 50 degree, why it is going to be stopped? Because had there been no spring, obviously there would have been a motion till there is a the gravitational effect that it is going to be stopped. But since there is a spring, you see here that spring will elongate and thereby will try to bring it back to its original equilibrium configuration. So as a result, there is a fighting between the two types of forces. One is force due to gravity, which is trying to disturb it from its and make the rod moving out from its initial position, and there is that restoring force which will be offered by the spring, which will always try to bring the rod towards its initial position. So because of this, there will be an angle intermediately where the rod will be momentarily stopped, and let us suppose that in this case that angle is going to be equal to 50 degree. So if this is going to be equal to 50 degree, compute the necessary spring constant. For your computed value of k, what is the angular velocity of the bar when theta becomes equal to 25 degree? So that is the second part of the question. Let us first try to answer the question in the first part, for which case it is being told to us that when the rod swings through by an angle of 50 degree, it comes and momentarily comes to a stop. So I therefore consider the initial configuration here as 1 and the final configuration, which is here is 2. And in this case we note that this is our center of mass of the rod, which will be at the middle point because it is said that it is uniform rod. So it means that the center of mass will be at its middle point. That means this length will be going to be equal to 0.4 meter. And with respect to this initial line, which we take it as our datum, this is going to be our height of the center of mass, and since it is below, this h bar is actually going to be negative. So we have h bar, but in the work equation when we are going to substitute, this h bar needs to be preceded with a negative sign because we are going to a position which is below the datum level that we have selected. So between these two positions, if we apply our work energy equation, we note that the reaction force which is associated here, we see it is not contributing anything to our work function. Why it is so? Because this is actually, these reaction forces are associated with immovable support points. And since it is associated, they are associated with immovable support points, that means they do not have any displacement. That means the reaction lines of actions of the reaction forces are not having any displacement. So therefore their work contribution will be totally zero. So in the active force diagram, we see there are only two things. One is the force due to gravity, and another will be the force due to spring. If we take this spring out from our system and just replace it by the instantaneous tension in the spring. However, if we include this spring also into our system, we see that there is no external active force that is present in this case. So as a result, again, this 1U2 is going to be equal to 0. So in the exam, you have to actually explain why this 1U2 is 0 here. So you need to mention 2 points. One, that the reaction forces associated here with this hinge or pin are actually, associated with immovable support points. So therefore they do not contribute anything into the work. And the second thing is that apart from the gravity force, there is no other, the active force that is present in the system, and as a result, we see this 1U2 should be equal to 0. And again, you see the sum total of the kinetic energy, gravitational potential energy, and the elastic potential energy is going to be conserved. However, since we have chosen the initial configuration as the datum, and initially the system was at the condition of rest, so I see, and also initially the spring is also unstretched in the initial configuration. Therefore every term of the energy will be basically 0 at our initial condition. So energy cannot be 0 actually, but kinetic energy can definitely be equal to 0, but other energies cannot be equal to 0. But it is actually not the instantaneous value of the energy, but the change in energy actually matters. So we see the way we have chosen our datum, we note that all this initial part is going to be 0. And also at position 2, since the rod is observed to come to a halt, so it sees therefore the final kinetic energy is also going to be 0. So as a result, we simply have the simple equation that we will be left with tells us that at the final configuration, the gravitational potential energy of the system plus the elastic potential of the energy of the system, they are going to be equal to 0. So again, I told that since that this height was actually below, so I have this is as minus mgh bar. So it is minus mgh bar plus half kx2 square should be equal to 0. And since our objective is to find out this k, so we can solve for k and can write the equation as 2 mgh bar divided by x2 square, where x2 width actually represents the elongation of the spring because of its final configuration. So you see from here that it is pretty simple from the geometry of the problem to note that h bar is going to be 0.4 sine theta, or it is going to be 0.4 sine 50 degree for us. That is the first thing that we need to know. Second thing, we need to calculate the extension of the spring. How we are going to calculate the extension of the spring? x2, that should be equal to L2 minus L0. That means L2 represents the length of the spring at the final configuration, that means the distance AB, and L0 that represents the initial spring length when you remember that the rod was perfectly horizontal. So in that case we see that the configuration of the rod is something like this. This is the rod and somewhere here is the spring, and the spring is connected like that. So this is going to be our L0. So it is quite simple to note that our L0 is root 2.6 meter, and the length AB from the geometry we can see that it is going to be 0.6 sine 45 degree plus theta by 2, which is going to be sine 70 degree, and the length becomes 1.2 sine 70 degree meter. From the simple geometry, because it is an isosceles triangle, OA equals OB, this is an isosceles triangle, so we can definitely calculate the length of the base when this angle theta becomes equal to 50 degree. So accordingly, we can see from this equation, we can find out our x2. That means we can find out the extension of the spring. Now, having found the extension of the spring, if we substitute all these numericals into our above equation, we note that the spring constant that we are looking for turns out to be as 92.68 Newton per meter. So this is our desired stiffness of the spring that we are going to use. So this is our first part of the question ends here. Our answer becomes complete because we have been told to find out the stiffness of the spring when the system will stop at an angle theta equal to 50 degree. Now we go to our second part. We address our second part of the problem, which tells us that for your computed value of k, that means the value of k that we have just now computed, what is going to be the angular velocity of the bar when theta becomes equal to 25 degree. So in that case, when theta is equal to 25 degree, the bar will be still in motion because it is actually supposed to come to a stop, momentarily stop position when theta becomes equal to 50 degree. So in between, it will be in motion. So actually for theta equal to 25 degree, the rod is or the bar is going to have some angular velocity. So let us represent this here. So this is the figure that we have again repeated for your convenience. Now we take theta equal to 25 degree. We see here, we need to mention here that theta is equal to 25 degree in this case, and we have some angular velocity. Obviously that angular velocity is going to be clockwise in nature. So again we simply just calculate for theta equal to 25 degree what will be the length of the spring. We know the initial length of the spring, so we call it the intermediate position. We know that this is the intermediate position when theta becomes 25 degree, but for us this is actually the final configuration. So because we are actually computing the things between this configuration and this configuration, so I call anything other than initial, we call it as final. So although it is not absolutely speaking is not the final configuration, because the final configuration would be the case when the rod will come to a position momentarily to a stop. So since it is the intermediate one, but for us we can call it to be the final position. So we see that the spring extension for this final configuration is now going to be equal to L minus L0, and that if you calculate it is going to be 0.164 meter. Now between 1 and 2, if we compute the work energy equation just like the previous one, we have all initial part was 0. So I have half IO omega square plus mg h bar. Remember, this is going to be our datum level. So this is going to be our datum level, and h bar, we need to, in place of h bar, we need to put a minus sign. So this is actually it's not going to be plus, rather we should write it here, as minus, because our initial final potential the configuration is below the datum level. So we put a minus sign here. We write that it is half IO omega square minus mg h bar plus half kx2 square should be equal to 0. And now if you substitute all the values, remembering the fact that I bar is going to be equal to 1 by 12 ml square, and IO, which is at the situation here, it is going to be equal to 1/3 ml square. So if you remember these results, we can come and substitute them, and numerically if we solve it, then if we put all numericals and if we solve this omega will turn out to be as 2.41 radian per second in the clockwise direction. So this will be therefore our desired angular velocity when theta becomes equal to 25 degree. So as it goes further with this stiffness k equal to 92.68 Newton per meter, this rod is designed to come to a stop when theta increases to 25 degree to increases to 50 degree. But again, if you change this value of k, definitely some other different angle will be the absolute angle or maximum angle the rod will undergo, and everything will therefore is going to change. So dear students, this particular problem highlights you the application of the work energy equation with pure rotational motion. However, in this case our rotational motion is non-centroidal one, and I am sure and confident that if you are given any centroidal rotation problem, it will be a very cakewalk for you, because that will be more simple situation, because you don't have any the linear velocity of the center of mass associated with it when your rigid body is undergoing fixed axis centroidal rotation. So we now move on to our next problem, which is highlighting it's a good problem. So let us identify this problem as a little bit involved one. So this is going to be our today's our last problem, which states that the two identical links. So there are two identical links. Suppose here OB and AB, each of length B and mass M may be treated as uniform slender bars. So basically they are slab-like bodies. Now if they are released from the rest in the position shown with end A constrained by the smooth vertical guide, so it is in vertical plane, so there is a G acting downward, determine the velocity V with which the end A reaches O with theta essentially 0. So theta is of course the angle between the two between these two links. So when theta is when theta is essentially equal to 0, that means when these two will collapse and will fall on this horizontal line, what will be the velocity of NA with which it will come and strike and it will reach the point 2. So we just assume that it is going to hit the point O. So before these two will actually collapse each other and will make a line, and we are just going to consider that O and A are going to be just coincident with each other. So if we look at this system in the problem, we see that it is a system of rigid bodies, because we have two bodies interconnected with each other. That's the first observation regarding this problem we have. Secondly, we note that the body OB, correct? This is actually undergoing pure rotation about the point O, which is again non-centroidal rotation. And the link AB, that means the other rigid body, it is actually, undergoing general plane motion. So we try to solve the problem in two ways, because we noted that when we have a rigid body undergoing the general plane motion, we can calculate the kinetic energy in two ways. One, we can go for the instantaneous center, or we can apply our classical equation for kinetic energy, general expression for kinetic energy that we have learned so far. So in the first method, we are going to approach it by applying the classical kinetic energy equation. So in order to do that, we have to do actually certain mathematical operations. First of all, let us try to identify for the link AB, which is undergoing the general plane motion. This is its center of mass, correct? Which is, of course, at the middle point of this link length AB. So if we place an x-axis and y-axis with its origin at O, that means these are your inertially fixed reference frame. So from that inertially fixed reference frame, let us try to identify the coordinates of the center of mass of this body. So we note that the center of mass of the body here is x bar g, which is equal to b by 2. You know that this angle we call theta, and since this is an isosceles triangle, we can call this angle as phi, and evidently phi is going to be 90 degree minus theta by 2. And as a result, we see from here that x bar g, which is simply to note that it is going to be b by 2 sine phi, because this is b sine phi, and since this is the middle point, so this length is going to be half of it, so it is going to be b by 2 sine phi, or it is b by 2 cos theta by 2. And exactly in a similar manner, its y coordinate of the center of mass of the link AB is being given by, this height, I mean to say this height, which is, of course, this is b cos phi. To it, we need to add this extra height, which is half of this height, that means b by 2 cos phi. So therefore, if we add them, it becomes 3b by 2 cos phi, or in terms of theta, we can write it 3b by 2 sine theta by 2. Now, having got this x bar g and y bar g, I will be able to find out the center of mass's velocity, and this we are doing by what is called absolute motion analysis technique. So we found the coordinates of the center of mass of this rod, and now we are going to calculate what will be its velocity when theta tries to vary. So we see it will be just x bar g dot square plus y bar g dot square. So you need to differentiate this equation with respect to time, noting that this theta and phi both are functions of time. So if you do this differentiation and add and square it, we find that this is going to be our expression v bar ab square for any angle theta. We can write this equation will be b square theta dot square by 16 into sine square theta by 2 plus 9 cos square theta by 2. So that is very good. So it is actually giving me the square of the velocity of the center of mass for this rod for any angle theta. Now you see, as the motion evolves, you see we are going to look for the situation when theta is equal to 0 degree. So under the circumstance when theta is equal to 0, that means when this rod tries to become horizontal, AB rod tries to become horizontal at theta equal to 0, what would be the velocity of the center of mass of the rod? So evidently that we can find out. By substituting theta equal to 0 in this expression. So if I put theta equal to 0, we see that the mass center's velocity square, the square of the velocity of the mass center, V bar AB square, is actually being given by 9 by 16 into B square into theta dot square at theta equal to 0. Right? Theta dot square at theta equal to 0. So that is the case of the velocity of the center of mass of the link AB. We will require square of the velocity of the center of mass of the link AB. We will require this velocity expression, square of this mass center's velocity expression, for evaluating its kinetic energy. So that is number one. Number two, we need to actually, our objective is to find out the velocity of point A. So let us do, before that, we also calculate what is the angular velocity of this link OB. Now, you see from here that the angular velocity of the link AB will be definitely equal to phi dot. Say, let us suppose phi dot, it is equal to minus half theta dot. Don't worry about this minus sign, because we anyway requires the square of the angular velocity. And since actually theta dot is going to be negative, because you see that theta is actually dropping, and if with time the value of theta is decreasing, so theta dot itself is going to be it's going to be minus. So then we have a minus sign, so it shows therefore that this link OB is going to have an angular velocity in the clockwise direction, because that is going to be for increment in phi dot, because theta dot is going to be minus, so this two minus will make it plus, indicating that phi dot is a positive quantity. So it means that phi will increase with time. So naturally that is only possible when you see that your link OB is undergoing angular velocity having by this particular thing. But you need to remember that we haven't found the angular velocity of the link AB. So that we are going to find little later. And also we see that since our objective is to calculate the the velocity of point A when theta becomes equal to 0. So let us try to evaluate again by absolute motion analysis what would be the velocity of A. So we see that YA is going to be equal to twice B cos phi, or that can be written as 2B sin theta by 2. So Y dot A becomes equal to B theta dot cos theta by 2. Again remember, theta dot is negative number. So Y dot A will be ultimately a negative quantity, which means that end A's velocity will be in the downward direction. So we see that if this is the expression for the velocity of the end A at theta equal to 0 configuration, we see that our Y dot A at theta equal to 0 will be simply B into theta dot, and therefore at theta, of course at theta equal to 0, because theta dot is not definitely constant, so it is B theta dot at theta equal to 0. So this is actually our desired. So that means we need to find out the value of B theta dot at theta equal to 0 situation. Also, before we proceed further, we need to see the angular velocity of the link OB, and we note that for the member OB we see Y bar G, that means the center of mass, this will be the center of mass, its height is B by 2 sin theta by 2, and of course omega OB equal to half theta dot, and already we have found omega AB, that is minus half theta dot, and omega OB is turning out to be as half theta dot. So it means that omega AB and omega OB, they are oppositely related. So what does that mean? It means that if OB rotates in the clockwise sense, then the member AB is going to rotate in the anti-clockwise sense. So that is, going to be our sense of rotation, because you see this is actually we note that it is half theta dot. So it is half theta dot, and in this case it is minus half theta dot. So both the two angular velocities will be actually oppositely directed to each other. Now we apply the work energy equation between these two configurations, and remember that we have two bodies, so we therefore use that grand sum equation, and also noting the fact that in the active force diagram there is no external force acting in the system, because all forces are the forces due to gravity, which we have already taken care of here, and we don't have any spring, so this term will be essentially going to be survived here. However, we have retained it, but this term is not going to be survived there. That is number one. And number two is that we see all other forces are related with non-immovable support reactions, so they are not going to be written here. So it is therefore going to be written for each particle, and this is going to be written for each particle. So these are, the conservation of total energy is acting. So we have, this is the equation, because your delta T plus delta Vg plus delta V is equal to 0. Now since we don't have any spring, I can simplify further this equation into this, and let us try to evaluate this expression for position 1, that means for the initial position. So remember, the initial position is this given geometry. So this is the initial position. So we see therefore that our initial position, we see it is 0, the kinetic energy is 0. Then we see from here that for both the links, because it is to be summed for both the members, so this is 0 plus 0 refers to the total kinetic energy for the two members, and then you see this is the total gravitational potential energy for the two members. And we should note that we are actually considering this x-axis as the datum for calculating the gravitational potential energy, and all CGs or the center of masses location are in the above position from the datum, so all of them should be turning out with a plus sign. So therefore you see this is going to be 2 mg b sin theta by 2 on simplification, going to be total initial gravitational potential energy. And at position 2, when everything comes flat, the gravitational potential energy will be 0. So this will be 0 plus 0. In fact, this will be actually the gravitational potential energy for the two particles, and this will be the total kinetic energy for the two particles. See, now for the first body, which is say for the member OB, it is pure rotation about 0.2. So we can just apply the relation half I-O omega square, in this case omega OB square. And for the second particle, we apply the classical energy, kinetic energy equation. That means half m v bar AB square plus half I bar, so this is I bar, into omega AB square. Okay. Now we just already calculated v bar AB square, and also we have calculated omega OB and omega AB, and we noted that the magnitudes of their angular velocities are essentially equal. So I can therefore see from here that it is going to be 1/3, and this is the final configuration, means at theta equal to 0. So straight away, actually these are all referring to this theta dot square. All these are actually referring to at theta equal to 0. So we see naturally. So we see that it is going to be on simplification, that if you put this and this half, I just take common and multiply it here, then we see from here that it becomes b square theta dot square into 1/12 plus 9/16 into 1 by plus 1/48 is going to be this, which when simplified, you see b square theta dot square comes out to be as 3 GB sine theta by 2 into 4. That means it is 6 GB sine theta by 2. Please remember that b theta dot square at theta equal to 0 actually represents v square a. So actually in place of this I can write va square at theta equal to 0, and this is 6 GB sine theta by 2. So we see that va at theta equal to 0 is given by root over 6 GB sine theta by 2. So this is the classical method by which we have solved the problem. The problem could have been also solved by using the instantaneous center of the member AB. See, the member OB, it is clearly well defined. We see that this is going to be the half theta dot. So this is the angular velocity is half theta dot, and for this member this is going to be half theta dot also. So these two are having the same angular velocities, so we have that situation. So we see from here that let us now locate the instantaneous center for the member AB. See, this member NB is having a velocity which will be going to be, in this direction, and this end is having the velocity in this direction. So at any general configuration, you see the instantaneous center will be here. So how we can locate this instantaneous center? That is pretty simple, because then this distance is going to be 2b sine phi or 2b cos theta by 2, because we extend it and just simply follow the geometry to note that triangle ABI is going to be isosceles, because this angle and this angle are going to be equal. Very simple. Just look at the geometry, identify that the triangle ABI is isosceles. So we see that this length is going to be B, this is B, so it is totally 2B. So naturally this AI becomes 2B cos theta by 2 or 2B sine phi, which is also 2B cos theta by 2. Let us assume this distance IG, G representing the center of mass of the member AB. So IG, this distance, if I call it as A, then we can apply this in this triangle IAB. In this triangle we apply Apollonius theorem, because we note that IG is the median of this triangle AIB. So apply the Apollonius theorem here to note the value of A. So this is Apollonius theorem being applied, and we see that A square becomes equal to B square by 4 plus 2B square cos square theta by 2. So as a result, I can see that I about this point will be given by, this particular equation, that is 1 by 12. Here about this axis it is 1 by 12 AB square. Now we need to parallel axis theorem, we need to shift. That means we need to add to it MS square, where A square is being given by this. So if you simplify this equation, we find that at any arbitrary configuration, I about of this member about the point I is being given by this equation. Now we are actually looking for the case when theta is equal to 0. So we can therefore say that at final configuration, so we can write like this: at final configuration, where when we see that theta becomes equal to 0, I find that the I about I of the member I about this member AB is going to be equal to theta equal to 0. If we substitute, it becomes equal to 7 by 3 MB square. So that is going to be my I when this member comes and becomes totally flat. So we see, therefore, we just write our equation. We remember that our equation consists of the total kinetic energy is equal to the change in gravitational potential energy. So in this case, the total kinetic energy will be half into 1/3 mb square into theta dot square by 4, because this is theta dot by 2 and that one also is theta dot by 2, plus it is half 7/3 mb square into theta dot square by 4 should be equal to twice mgb sine theta by 2, which we have already derived in our equation. You remember where from we have got this equation? We get this equation from this here. See, this is the equation, because you have only kinetic energy survived in the final configuration of the system. There is no potential energy, gravitational potential energy associated with it. So it is simply written by this. So we can take this half etc. common and can write from here. In fact, it is 1/8 can be taken common. In fact, it is not only 1/8, it is actually 2, 3, 6, 24. So 24 can be taken common, and therefore we can write this is mb square theta dot square plus 7 mb square theta dot square. That means it becomes 8 mb square theta dot square should be equal to, this is 24 into 2, that means 48 mgb sine theta by 2. mgb, sorry, one b is extra, so just remove it. So it is mgb sine theta by 2. And we can write from here that b square theta dot square is equal to 6 mgb sine theta by 2. So ultimately, you see, this is representing the velocity at point A of point A at theta equal to 0. So this is theta equal to 0. So we see that this equation becomes 6 mgb sine theta by 2. So we can write from here that VA is going to be equal to so VA is going to be equal to root over 6 mgb sine theta by 2 in the downward direction. So we note from here that this second method is more, algebraically more neat. Only thing here, you need to actually conceptualize the situation and need to calculate your I about the mass moment of inertia, about the instantaneous center, and at this particular position you need to see when they become flat, one being superimposed on another, we need to find out what should be actually the the angular velocity of the entire system. So dear students, therefore with this problem, the last problem is little bit elaborative one, which it shows you the basic concept when you have two or more rigid bodies getting interconnected with each other, and for a particular type of motion, how you are going to apply your work energy to solve your problem. So I hope that with these three problems you have understood the basic concept of the work energy equation, which can be applied, the principle of work energy that can be applied to a rigid body. So with this idea, I will invite you to solve few problems from the book in order to master this concept. Thank you. We stop here, and thank you once again for watching the video. It's bye from my end.